It's a pleasure to have Chuong Tran talk today, and he's going to talk about velocity pressure correlation in Navier Stokes flows and the problem of global regularity. Thank you, Chuong.
Thanks everyone for coming. Good afternoon. I'd like to thank the organizer for having me here. This wonderful program, Cambridge, is always my dream of visiting and working here. So thanks again. Today, this seminar, I will discuss my recent work on velocity pressure correlation and its role in extreme roles of momentum, and that's determined regular or similar Navier Stokes flow. And this work is a joint work with Xinwei and David Dritschel. Xinwei is a PD analyst from Alberta. David Dritschel is a numerical expert in science rules. I am a physicist by training from the middle of nowhere. I have retired science rules and now free man. Okay, so velocity correlation and velocity pressure correlation and its role in extreme role of momentum in Navier Stokes flow. Okay, the Navier Stokes power plan. Set this quantity to 1 for convenience. And we consider this one in R3. And maybe the time interval from 0 to some capital T. And you got initial velocity field. It is assumed to be smooth. Force divergent free. And we know for sure that smooth solution will persist at least for some time t here, which may be small, but there's some time t which is non-zero. That solution can be smooth. Beyond that, we just don't know. But the question is whether the can be continuity or similarity can develop as some T star. We are concerned with. Okay, so let me give you some background about this problem. Since the work in 24, we know that if singularity develops as some t equals T star, then we must have this rule of the LS norm of U. What is then some constant divided by this number right here. S minus 3 or 2s. And this is for s greater than 3. And this happens when t is approaching T star. And maybe CS here also may depends on S. Somehow I just take it as absolute, but I think it's more sensible to make it dependent on S. And I think that's what Louis said in his work. So maybe some dependence on S right there. So you see, this practical result doesn't address the K S equal to 3. And that case has been tackled recently by House. And I think it's in 2019. So L3 must diverge in this way. Leave self T go to T star of 3 here divided by equals further 3. 3 divided by this equal log. Some positive constant C could be large, small, doesn't matter. Equal log. Mostly infinity. So in order for singularity to occurs at T star, we must have this. Okay, so this is well known. This is just the recent result, and you see this one is very similar to the very rapid result by Sergey and Sprak about L3, which I will just discuss in a moment right here. So these are two singularity criteria, and now I list some regularity criteria. So this is due to Ladies and Schuyler, Borty, and Sergey, and they did this 70, 60 years ago. So in order for regularity to persist until TUR, we must have this classical result. And then 2s over s minus 3 was the finite, and the integral respective term, and again s greater than 3. Then because s equal 3 is not included here, and the last case is tackled by Xinwei. So I think it's 2003 or 2002, perhaps 2002. Check. Yeah, 2003. Okay, essential agreement of UL3 looks finite. Then we have regularity up to this T and maybe beyond. Okay, so these are classical results, well known, except the recent result by TUR. And it's similar for the pressure. We can replace this norm by the pressure, and we still have this regularity condition. T LS 2s over s minus 3 T. This is for the infinity of it, and s must be greater than enough. So we replace like u by p by u square to them. Okay, so another one, regularity, also due to Sergey and Sprak, you must have p bounded below. So p must not decrease all the way to minus 50, then you are okay. You have regularity. So look at this. You must have p goes to minus 50 in order to have similar. You must have blow up of velocity because of this. You must have blow up of velocity and also blow down of pressure. So for singularity, we require you to blow up P to go to minus 50. And this makes sense physically, because look at the now stopping person right here. The velocity is accelerated by the pressure gradient minus pressure gradient. So it just go and go and goes down to lower and lower pressure. Yeah.
Pressure to minus infinity. Is it 0.1?
Any points. If you have 1 point, it's
1 point.
it's singular already. That point, right? So you need just 1 point, point singular. It could happen on a very, very complicated set. We just don't know. But I think it should blow up point-wise. That's what I think. And a recent work by 3 Koreans, I think just a couple of years ago, they looked at singularity in the L3, weak L3. So slightly greater than the L3 space here. And they concluded that singularity could happen only as isolated points. So there is some justification for studying isolated singularity.
Also, pressure is defined up to constant, additive constant. So something was fixed in this sense. Otherwise, I can always add arbitrary constant to pressure and everything is fine. Just for form.
I don't get what you mean.
The pressure is defined up to an additive constant that can depend on time arbitrarily. Just grad of P. Sorry? Infinity. So, okay, then the pressure at other points will be infinite. Yeah. Okay.
Now, the acceleration is negative, the gradient. Right? But because of this singular regularity criterion, the gradient cannot diverge without P itself go to infinity, and it must go to minus infinity by Sylvian and Sprague, and I think that's 1 year earlier than this guy. And this paper, 2002.
His question, he says that you change P by constant to be still a solution, and then this integral might be infinite by just changing the constant. So you need boundary condition of P at infinity. Avoid this constant. That's what he's asking.
We always have decay at infinity fast enough, right?
I also read somewhere, and I didn't understood that this hypothesis that P doesn't go to minus infinity is related to the absence of cavitation.
Yes.
But this is an equation without density.
No.
Can you comment on that?
Yeah, I mean, physically, right? I mean, physically, the point is that physically this phenomenon will correspond to cavitation. Okay? But obviously, there's a transition phase if you have cavitation. The equations are no longer valid at something else.
Anyway, any form of singularity means that the model is not valid anymore. So you have to. So that's,
But
it's
I mean,
valid as
physically,
long as basically there's this.
Okay.
Okay. So because of this, I consider the velocity pressure correlation because velocity and the pressure must be strongly correlated in order to have very strong rule of momentum. So imagine if you have a low pressure center like this, fluid will be accelerated toward it. And it has to go into this one extremely fast. The pressure will have 2 degrees like this, and velocity, fluid particle will have to accelerate faster and faster and faster toward this. So the correlation, the maximum velocity here, and the minimum pressure must be strongly correlated. So they must come together in order to generate singularity. So that's the motivation for looking at the correlation between them. Correlation between maximum velocity and minimum pressure. And that's all about this paper that I studied. Okay. the result of my mathematical result.
Exponent is wrong. I don't know how it should be correct, but exponent might be negative.
Yeah.
Maybe S minus,
Maybe say half minus say half.
or 2S minus 3 in the denominator.
What's wrong?
In the exponent in the P, in the integral of P and S,
I think
this exponent should be different. Maybe it should be 2S.
2s, yeah. Sorry.
It's okay.
So you replace p by u squared. Yeah, 2s like that. Yeah, oh, thank you. Yeah. So here's some of my mathematical results for the paper, and that's mathematical result is not much, just some improvement of this practical result right there. I just use velocity pressure in here and then add the correlation and then divide it by L3 norms for this. And that's will take about a page to prove. But the mathematical works will clarify the correlation that I studied. Okay, so I look at the evolution equation for LQ norm in general of U. And this is the pressure term to the right hand side, the advection term is superior, and we have the forcing term due to pressure and dissipation term due to viscosity. Q minus 2 in row over R3 T U Q minus 3 U dot with the gradient of velocity, right? And then the dissipation term broken up into two pieces. U Q minus 2 over 2 gradient of U. This is L2 square and another term. So here,
Can you lift the up?
So this, okay.
U here, Q minus 2 over 2, the gradient of U L2 square. So this is the forcing term, just multiply the absolute expression by some power of U, Q minus 1 power of U, and then integrate by cos the forcing term, and then the expression comes out like that. So I can put this one into here because this gradient is better than this one. So I can just remove this, and then this one is just one now. So okay. And you see here there will be a correlation between P and this. So I can break the partition R3 into the left. So this is omega, and within omega here, U will have to be greater than some constant C, maybe depending on time as well, but not necessarily constant. U LQ. I partition R3 into these two region with high velocity and region with low velocity. And the convolution to the forcing term here from omega C can be annihilated by a fraction of the dissipation. So this is Q minus 2 0 omega plus Q minus 2 0 omega complement. Then we minus the displacement term. I can cancel this one by maybe half of this. So this will be Q minus 1 minus sine over 2 U minus 2 over 2 radius of U, and then L2. It can always be done. So the forcing term now just concentrate on very small region, narrow region, and this region will have to go to 0. The measure of this will have to go to 0 when I have LQ go to infinity. So in this sense, the singularity set will have 0 measure, and that's well known. As people have done this, but this is very easy to demonstrate that the region here, the driving region, will have to be smaller and smaller when you have more and more stronger momentum. Function here, maybe depending on Q for sure, depending on T as well. And this will have to go to infinity as well. Okay, so the region of the forcing will have to be very small. Not only this one will go to infinity, but this guy will have to go to infinity as well. So this will be very large on the way to singularity. So in some sense, this region getting very small very quickly. Okay. If I take Q to infinity, then CQ here go to 1. Okay. So infinity and this will go to 1. So in some sense, the maximum velocity will be accelerated just by the maximum velocity itself. The rest is irrelevant.
What's the definition of CQT? What is CQT?
CQT is just a number that I picked before I partition this, before I partition R3 into 2 regions. And after that, I will figure out how big C should be in order for this term to be controlled by this. And that's determined C.
Is that CQT the same as the C above?
No. It's different.
Okay. The CQT is different than the one above.
This CQT,
That C is it related to the?
They're the same.
This is
They're
just
the same
functional.
constant.
It's
the same constant.
And then, but it's a special choice.
For this Q or for this T.
And you specify Q, you specify T. Give me the value to put in that inequality to define omega.
Yeah.
I think.
so the definition of omega depends on this one. And this one is figured out after I try to control this by the displacement term, the half of it, and that's determined C. So this CQT is well defined. And the properties, I just want to quote it here, the property is this. So for finite Q, and if singularity occurs, then CQ will have to diverge from the formula that I derived for C from that. So not only this one diverge, C also diverge, and we will have very small omega. Omega will have to be very small. Okay, so I can use just Cauchy-Short inequality to break this one up, and the L2 norm of this guy to some power like this will have to be brought out because of the displacement term right here, and I will be left with this. Equal to Q over omega T square U Q minus 2 dx. And then the distinction term I use superlap inequality, and I will get 1/2 C naught Q U L 3Q and power Q. Superlap inequality from this to that. So superlap inequality in R3 C naught radius of F 2. Okay, so Hawking term, the spacing term. And at this point, if you replace P square by U fourth, then you would have this, a constant, and then 2 cubes in there, over there, U Q plus 2 dx. And the distribution term.
Really switch the words.
Yes.
You can always do this by
You know, the upper one, going down in distance. The upper board. It's
Yeah,
not
this
this
one
one,
is-
going down, and down, down,
Oh.
going down.
different orders.
Down, yes.
That's how you.
You can always do this, replace P square, P by U square, by current Sigma inequalities under the integral sign. Okay, but doing this is bad, really bad. I don't want to eliminate P in terms of Q alone, U alone. This is bad because you would lose the correlation between P and U. Okay? I need to keep that. And it is a simple motivation for keeping the correlation. So this one, what I don't want to do. But I think up to this point, this is always the case because we don't know much about the pressure. We only know the pressure through the current Sigma inequality, so express the pressure in terms of U. And we also have the Poisson equation. And this seems to be no further knowledge for P. So normally we do this to estimate that interval. And this is actually what I did until this paper. I realized that doing this is not very good. And I will convince you by this very simple example. If you look at a function psi like this, 1/x minus x naught, and I take it square the power 2 here, and another function 1/x over x naught 1, or maybe put this x1 and this one x2 power 1. So this is like pressure at the critical scaling of Navier Stokes 1/x squared. The pressure should scale like that in the invariant scaling of the Navier Stokes equation. This is like the velocity 1/x critical scaling. And if I look at this interval, then I have the graph the epsilon equal to x1 minus x2. So I have x1 right here, and then x2 right here. This one is non-zero. So the two of them, psi and phi, are not perfectly correlated. I mean, when the two singular peak here coincide, and that's what I call perfect correlation. If this one is more imperfect, high correlation but imperfect, and this epsilon is large, they are not so correlated. So this is a measure of correlation symbol measure. And you see this when I have this not perfectly correlated. This one is finite for sure, because power 3 right here, 1 over x cubed. But since this one is not 0, I'm okay. But if you try to estimate this guy, my symbol goes short of the body. And this is what we usually do. And then the integral I square dx 1/2. This one is okay. This one is finite. This guy blow up. This guy diverges very, very fast. So it's no good. This estimate is no good. Same as you decouple P and U. You decouple P and U, you suffer almost the same thing. If P and U not perfectly correlated. So another estimate, maybe a little better than this, but still no good. You have integral this 3/2 dx. And this is integral of 5 3 dx. So this is 2/2. That's 2/3. And this is 1/3. Coefficient of the body holder is 40. This is not good either, because this guy will diverge logarithmically. This is 1 over x cubed, and this one 1 over x cubed, and x go to 0. So we go to infinity. This also go to infinity. You use infinity to bound a finite number. So it's not correlation between P and U, very, very important. Extremely important. If I don't have perfect correlation between the two, then I certainly have regularity. Similarity cannot develop when the minimum of P sits in here and the maximum of U sits in here. Apart, they have to come together in some way. But if they are a priori perfectly correlated, if they coincide, no similarity either, because the maximum velocity is sitting at the minimum pressure, no acceleration. No acceleration if you have that case. So perfectly correlated is no good, still regular. Not so strongly correlated, regular. Similarity only happens when the maximum velocity approaches the minimum velocity pressure in some way. And that's the big problem that we have to understand. How the velocity will have to approach the minimum pressure, and minimum pressure will have to go to -50 in order for similarity to develop. So the condition for similarity is very, very extreme, very hard, not very easy. Okay, back to my mathematical results. I have this. Okay, UP for the maximum equation smooth, and we don't have this. Regularity, if I have this, gamma 3, I will define gamma 3 in a moment. 9 minus s over 2s minus 6 u ls 2s over x minus 3, and I divide this one by u l 3 cubed in t. Okay, if I have this, I will have regularity up to big T or maybe beyond. Another one. This is true for S from 3 to 5. would be fine.
What is it, gamma 3?
Hmm?
Is it the gamma 3?
Gamma sub 3, I will define it. I will define it. Is a correlation function between P and U. Okay, so this is gamma 3, U, L, S, 2S over S minus 3 divided by U, L, P. The power is now not 3, it's 6 over S minus 3 dt. And this is for S greater than 5. And so I don't know why you pass 5 and the denominator difference, we just don't know why. The mathematical results that tell us that we don't have no idea why there is a split right here at that point. Okay, gamma 3 correlation function between actually gamma Q. I have just for general. Here I consider the case when Q equals to 3. But in general, we have this correlation function defined as 0 over there, that's the blinding set over there. U Q minus 2 x over 0 R3 U Q plus 2 yes, and we know that this one is finite for sure. So this one is like Q plus 2 right here. But as I said, from the motivation, this could be very small. Could be very small on the way to similarity. This could be very small. If I have this, then regularity will persist. Regularity persists, cannot develop. But no hints how to achieve this, how to do this, but this is what I guess. Okay, so look at the result right here. So it's just some small improvement of the maybe non-scalar Rodney and Serbian results. Here I have just this factors into there. Okay. One improvement, this denominator. Right? This denominator, when you have similarity, they will have to blow up as well. So this is a big improvement. People before me, they have some other improvement like log, and the denominator some log, but this is a very significant improvement of this. So with that denominator is one improvement, and that improvement actually due to a previous paper between me and Xinwei, not from this paper, a previous one. So this result is a copy of the previous one, except I introduced that correlation. So this is another improvement. I have this correlation here, sitting there, which could go to 0, which could be small in the similarity limit, which is small. So two improvements for the classical results that I reported in this paper. So that's almost it for the improvement for the mathematical results, together with the partition of the space into the singular region, which is omega, which has to go to 0 very fast. And I said only two improvements over there. The rest of the paper is just about the correlation that I'm going to discuss right now. Pieces of log. And I will return that I have tried to convince people that Navier Stokes is regular, and hopefully they will come up with some proof someday. If you all need to see the proof. The proof will not be from me, could be from my collaborator there, Xinwei. He is a PE analyst, so the wonderful mathematician. Okay, this is the dynamics of flow. I have negative pressure here, and I wish I don't want, but I wish this could go to minus 3. You'll see star that's for blow up. And look at this. How could good particles approach this one? If I have this approach, and the streamline will end up right on this minimum center, then I don't have incapacity. Because I have acceleration into here, and I ended up in here, and this act like a black hole. Cannot, no particle can escape from this center, and if I have just a particle coming in head on, certainly I would not have incapacity. This guy cannot accommodate any incoming particle, incoming material. So I may have something like this coming in and start off, but cannot go out because of the negative infinity pressure center. So this has to approach this one and infinite velocity and not ended up there, but scatter off in some way, but cannot go any far. Imagine if this could happen. So the streamline will have to end up somewhere, not on the minimum pressure. Can you imagine that dynamics? A particle should streamline go like this and then terminate not on the minimum pressure, but terminate next to that. That's very difficult to imagine. Right? So if I have something like this, it could be okay, but it's very difficult. Infinite acceleration, scatter off like that, and cannot go far away from it. And another thing is that you have the Poisson equations. Okay, you need this Poisson equation. But the Poisson equation, I just want to bring it up here. Some of you may write it in some other ways, but I find this way of writing the Poisson equation is very neat, very nice. So this is square minus the velocity rate square. Poisson equation for the non-linear, the non-zero term on the right hand side is exactly that. Yeah. You integrate this over space, of course, you rest your own. After you don't need the Poisson equation, you just have to use the divergent theorem in order to have this. So, singular dynamics, you have minus infinity for the pressure. The pressure will have to blow up like minus 1 over x minus x naught, or maybe just x. Look at the singularity at the origin. Alpha, and alpha must be at least 2. Alpha equals 2 is the critical scaling for the pressure. So in order for singularity to develop, I must have the pressure blow up like this. So this pressure will have to blow up, and this is strong. Right? So if the pressure blow up like this, the Laplacian will have to blow up like 1 over x to the alpha plus 2. Okay? And if I have a point like this, I must have a positive maximum here also go to infinity. Otherwise, I just don't have that. And this one must be another actually. But if I send a post, there may be something they separated for sure. So now the pressure going to minus 50, or the pressure we have to go to plus 50 somewhere else. Okay. And if I have this, it's even harder to imagine the dynamics around this high pressure center. High pressure center, fluid we have to go away. Infinite velocity to go away. We don't have material right here. We have not gone away. So there must be something like this. So fluid will approach this. For some reason, I don't know. I don't have mechanism for this approach. How can a fluid particle approach a higher and higher and higher pressure region and ended up right here with zero velocity and then start off with infinite velocity? Similar to this case, if I have just a particle approaching this, ended up right here at zero velocity, I would violate this incompressibility. So it must start off like this in order to reserve the incompressibility. So this is already hard to imagine. I think this one is even harder to imagine similarly. This will have to go to zero. Okay. And you have to go to infinity. You go to infinity, and here you go to zero. So that's my picture for singularities. So a priori, total correlation between minimum pressure and maximum velocity is ruled out because the maximum velocity is sitting at right here at the minimum pressure, no acceleration. Only approaching is allowed for singularity, approaching in some manner and then scatter like that in order to preserve the incompressibility condition. So there is another thing. Of course, I don't have any mechanism for the pressure to go to minus 3D or the pressure to go to plus 3D because the pressure, I think the pressure gradient acting like a restoring force. When flow happen in some way, create a low pressure, and as soon as I have a low pressure center, fluid just try to jump in and to weaken the pressure gradient, not to strengthen it. So how come the pressure gradient can be strengthened to infinity? I don't have a mechanism for that. As long as you have a pressure gradient, fluid will just try to erase that gradient. That's the motion of fluid. It's driven by negative pressure gradient, and by that the fluid will flow in order to weaken the pressure gradient, not to strengthen it. So there is no mechanism for this, and even if somehow I have this one decreasing, the pressure here decreasing, pressure here increasing, I still cannot visualize how the velocity can end up infinite velocity.
I think you're saying it because you're limiting yourself to the board, to dimension. There's a third direction.
Yeah,
This would be going here and going the other direction. It's three-dimensional picture, not two-dimensional. So probably this picture is really beautiful and nice and correct to the case. But in 3D, your third direction, it's not only coming this way. You can come this way and go that way and go all kind of directions.
But was this why sparkling's model, right? It was invisible, but this argument is in.
So actually, this argument doesn't depend on the dimension. I just look at a single streamline. So that single streamline just lie in the plan approximately. Single streamline. That single streamline just passed by a minimum pressure, or this single streamline will get like approaching a maximum pressure here, minimum pressure. Just look at the single streamline like this. It relatively, I mean, approximately, it lies in the plan. So this picture is actually not very bad.
No, I understand. I like this, is fine. But you know, the minute pressure trying to go to minus infinity and you have singularity, the model breaks, even divergence equal to 0 breaks, everything breaks. And therefore, I mean, you cannot keep one thing holding and the other one is going. So it's all together. And that's why the argument is,
Yeah,
I'm not expert in fluids in the sense of like giving this beautiful description, which is I wish I could learn it more. But you know, I always visualize tornado as something where you have almost like singularity, but the pressure is very low inside. I mean, and that's what basically trying to push towards singularity. So that's why I thought the picture, if you look to dimensional, but there's a third direction. So that's why.
But actually, tornado is a slightly different.
No, I understand. I'm just giving it as an example of what's happening, the phenomenon that is swirling very much.
You have
The singularity and the pressure is very low. That's what I'm.
in the atmosphere, you have sustained pressure minimum. You have low pressures lasting for days and days, hurricanes or tornadoes. But that's because the pressure gradient is sustained by condensation of moisture. Without that, we don't have that condensed. We don't remove fluid from the system. In the atmosphere, we remove the moisture. So the low pressure center is sustainable for many days, but we don't have that in pure fluid without condensation.
No,
You
I'm
have to.
saying that the tornadoes, I'm just basically visualizing it as a Lagrangian picture. You know, I mean, I'm not talking about tornado as a phenomenon. I'm talking about visualizing the picture of this type in which the pressure is becoming very, very small in the center and you're swirling very quickly, and therefore you're getting towards singularity, which is similar to the pictures. And anyways, I would like to didn't mean to.
Yeah, actually, in fluid dynamics, when fluids come to a low pressure center, it's come like this. Now, because of incompressibility, cannot go head on because of the resistance from incompressibility. Driven this one sideways, and it will go like this. That's why we have vorticity rated around minimum pressure. But when you have vorticity surrounding this, the vortex just like shield the minimum pressure center, allowing no penetration of energetic fluid particle to come to that. So it's very difficult for fluid to approach a minimum pressure center because so just like a protection.
You're still viewing the vorticity as two-dimensional.
Up motion in the tornado, it lifts all the objects up in the tornado. It's very strong upward motion. It's spiraling in.
Have to go around. Perhaps in some weird manner, fluids that come in and then just put up in the third direction. But if you shoot up in the third direction, what is driven up? You must have low pressure center somewhere in order to have this one accelerate in the third direction.
Yeah, well, that's why the moisture.
And you need that minimum pressure to go to -3 as well. So it's not easy. Even if you have this situation, who is driving this one away to infinite velocity? We don't have any mechanism for that.
So
Oh, and actually, I was curious about what you said about what it had to do with Dwight's model. I mean, I see this plus and the pressure due to this. Can you be more explicit, perhaps?
And he just needs the pressure was really,
Oh, okay,
and the other one, pressure was.
okay, so it's not a question of the directionality.
If I remember his explanation, in a sense, it was the pressure not doing the singularity while the velocity was doing this, going into singularity. Because he was saying that the rotation was compensating the pressure which stops.
Oh,
This,
really? You think the pressure doesn't go to infinity?
Is hard for pressure, no physical mechanism to drive the pressure to minus 50 or plus 50. I don't see any physical mechanism for that. I said before, the pressure gradient acting like restoring force. So it's like a spring. When you spread it, you try to contract. When you press it, try to spring out. Right? So as soon as you have a pressure gradient, fluid will flow in to erase that, to weaken that gradient,
Yeah.
not to sustain that. I don't see any mechanism to sustain very strong pressure gradient.
Okay, I mean, I should know this better, but I don't know.
well, okay, I also should know this better, but
Well, I should really know this better.
This is a question from Vish. Anna,
I'm sorry.
it's a question from Vish.
No, I
I'm
was
sorry, because
sure,
I'm behind.
no, John. Maybe John has a question.
Oh, John has a question.
No, I was thinking maybe John.
Oh, maybe.
No.
John, you have a question?
Maybe he's.
Do you want to have them?
That's-
No, John is here.
No, he's probably.
Sorry,
John?
Yeah.
no, I don't have a question. I mean, I've been following the talk, but the light on the board means I can't read everything. So no, I don't have a question.
Oh. I will send you a photo.
I'll discuss with IT to improve the lighting.
Well, I see many
It's
people
okay.
took notes, so I assume we can send photographs of the notes.
Maybe
Yeah,
probably.
that's it.
In my paper, it's 18 pages.
Yes, I have the paper, I can check.
Actually, it's very easy to read. I wrote this one for JFM, right? So I have in mind that the people reading JFM not so mathematical.
Yeah.
But simply you said, oh, well, so hand waving. I said, okay, this is for JFM. David Dritschel,
So let's combination.
Remember Alice, okay, I don't understand. For me, I am a physicist, I know what physicists expect. And luckily, the editor just like it.
Shall we?
Yeah, absolutely. And we don't have a seminar list, that I know of on Monday, but we have 2 seminars on Tuesday.
Monday usually serves in
Yeah, there's a
which is
PD
announced only for, who's speaking on Monday?
Simon.
Oh,
So, yeah, one of us, so. Simon is looking on Monday.
and we have 2 classes. And tomorrow is.
Thanks,
Yeah,
boss.
I am not, I don't handle.
Tomorrow it's.
Yeah, there should be.
Because I'm talking.
Tomorrow is day, I know. Yeah.
The other one should be the workshop taking place in
Right.
Banff in Canada. Well,
Well, thank you for.
thank you very much.
Okay.
Oh, I see. And I want to, only Sunday. Why not? I'm not a busy guy.